we have one of the largest machines in Europe called it's an emulator. It's a rack of FPGAs where we can drop into this rack of FPGAs an image of the chip. And this chip will work at something like, let's say, 500 kilohertz instead of 3 gigahertz. But at 500 kilohertz, you can start the software. So the Linux kernel will boot in a couple hours. 3 hours in our cases.
And starting to simulate and see how everything is working here.
So that you will have a shell with you can have an hello world. You will see that the kernel will boot and will not add in kernel panic. It's a good sign. So it means that plenty of gates in the chip has already been used. You can start to have communication over PCI. But now the drawback is that in emulation, it takes time, but it's reasonable. So you can wait a couple hours, or if you send a batch on Friday, on Monday morning, you have the result of the emulation. And with this, you limit the risk because you can fix them during the design phase and not after the production. Because if you fix hardware bugs after the production, it's complex because it's a new spin and lots of expenses to do.
But basically, if you find a bug, you will need to fix the bug, then relaunch the simulation, which means like lowest cost of minimum bug in the design will be 1 or 2 weeks fix just to get the simulation results.
We have some so-called run which can take a couple of weeks, but anyway, compared to an issue in production, it's nothing.
And yeah, just to understand the feedback loop, because basically, if you are a developer, you just like write a web page, it refresh on the browser, and you have your feedback loop. But there, the feedback loop of something, it's about 1 or 2 weeks minimum time. It can be bigger for a bug untangling with memory and stuff. That will creating a long time to debug the stuff, which is elongates the time from an industrial point of view. And for sure, it's way less expensive than producing the stuff, putting the chip and say, oh, it doesn't. Oops.